Today, we're going to put on our detective hats. We're going to investigate how researchers figure out if one thing truly causes another, or if there's something else going on behind the scenes.
So, let's start with a classic crime scene. We see two things happening at the same time. When ice cream sales shoot up, assault rates also go up. It's a really clear pattern, right? They seem to be connected. Researchers would call this a covariation.
So it looks like a simple case of cause and effect. More ice cream, more crime. Case closed. But, any good detective knows you have to look for a hidden suspect.
And bam! There it is. Hot weather. Think about it. Hot weather makes people want to buy more ice cream, for sure. But it can also make people more irritable, more agitated, and that can lead to more assaults. The heat is the real culprit behind both things.
This hidden culprit has a name in the research world, a confounding variable. It's basically the master of disguise in our detective story. It creates this relationship that looks totally real, but it's just an illusion. So how do we unmask these variables and find the actual cause?
Well, to isolate our main suspect and really prove causation, detectives have an ideal tool. It's called the experiment.
And there's a reason it's considered the gold standard. It's specifically designed to rule out all those pesky, confounding variables. It gives us the absolute strongest evidence you can get for a cause and effect link.
Now, the secret sauce here is random assignment. It's kind of like shuffling a deck of cards perfectly and then dealing out two identical hands. This makes sure that both of your groups are as similar as humanly possible, so the only real difference between them is the one single thing that you're testing.
This really boils down the logic. By comparing these two paths, you can totally isolate the effect of your one specific action. If the outcome only happens on path A, well, you found your cause.
But here's the catch. This reveals a huge trade-off that every researcher faces. An experiment gives you super high internal validity. That's your confidence that, yes, you found the cause. The problem? Because it's a controlled, kind of artificial lab setting, the results might not apply to the messy real world. That's low external validity. For instance, a new teaching method might work perfectly in a small, monitored classroom, but then totally fail when you roll it out to thousands of different schools with different kids and different resources.
Right, so detectives can't always work in a perfect lab. Sometimes you gotta hit the streets. You can't randomly assign which countries get a democracy in, which don't, right?
So when random assignment is off the table, researchers have these other really clever methods. Now, they're not as perfect as a true experiment for proving causality, but they have much better external validity. They actually reflect what's happening in the real world.
The key technique for all of these real-world studies is something called statistical control. You can think of it as the detective's interrogation method for finding those hidden confounders. So let's open up a case file and see how it works.
Okay, here's our mystery. Does being more politically knowledgeable actually cause people to donate money to campaigns? We've got a hypothesis that it does. Let's see what the initial evidence says.
Whoa. Okay, at first glance, it looks like a slam dunk. There's about a 15-point difference between the two groups. But a good detective always asks, wait a minute, could a confounding variable, like say income, be the real cause here? Maybe people with more money are just more likely to be knowledgeable and more likely to donate.
So let's interrogate the data. We're going to hold income constant. That just means we look at one income group at a time to see if the relationship still holds up. First, let's look only at high-income people. And look at that. The relationship is still there. There's a difference of about 14 points, so political knowledge still seems to matter for this group.
Okay, now let's check out the low-income folks. And what do you know? The relationship still holds with about a 13-point difference. So here's the crucial point. Even after we account for income, political knowledge has its own separate effect on donating. Income isn't the whole story.
So after this whole interrogation, our detective can reach one of three possible verdicts about the relationship between their main suspect and the outcome. First, the relationship could be spurious. This is our ice cream and crime case, right? Once you account for the heat, that link between ice cream and assaults just vanishes. The initial suspect, ice cream, is totally innocent. And here's a perfect visual of a spurious relationship. So imagine we first saw a big difference between how Democrats and Republicans felt about gun control. But then, when we control for gender and look only at women, we see their support is identical. Doesn't matter what their party is. That means the big difference we first saw wasn't really about partisanship at all. It was actually about gender.
Okay, second verdict, it could be an additive relationship. And this should sound familiar, because this is just like our political knowledge case. Both knowledge and income seem to contribute to donations, kind of independently. You could say both suspects played a part in the crime.
Finally, we get to the most complex one, an interaction. This is where the effect of our main suspect actually changes depending on some other factor. It's not a simple story at all.
For example, the effect of your political party on your gun control views might be real, but it could be totally different for men and women. For women, the difference between the parties might be pretty small, say 7 points. But for men, it might be a huge 22-point gap. The relationship itself actually changes. So at the end of the day, every research design is a different tool in the detective's kit, and each one has its own strengths and weaknesses. There's this constant trade-off. Experiments are fantastic for proving causality in a controlled lab, but observational studies are often way better for seeing if those findings actually apply to the big wide world.
So now you're equipped. You're basically a research detective. The big takeaway here is to always question the obvious relationship. Ask yourself, okay, what else could be going on here? What hidden suspect might be lurking in the data?